Talking about AI, don't you know? Neural networks and deep learning too. In this podcast, we'll break it down for you. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data science models, we can't get enough. This podcast rocks, it's never too tough. Got questions, we've got the scoop. Join our tech savvy podcast group. From beginners to pros, come one, come all. Machine learning's fun, we're having a ball. Machine learning, oh what.
Hey there, everyone. Welcome back to another episode of AI at the Edge, the podcast where we dive deep into the world of artificial intelligence, machine learning, and how these cutting-edge technologies are revolutionizing various fields. I'm Aubrey, and I'm here with my enthusiastic co-host, Shastya.
Hi, everyone. It's awesome to be here with you all. Today, we're going to talk about something super exciting, combining machine learning with structural dynamics for systems with isolated nonlinearities. And yes, I know it sounds like a mouthful, but trust us, it's coolest thing since sliced bread. Stick around because it's going to be fun and fascinating.
We'll be discussing the paper titled A Structure-Preserving Machine Learning Framework for Accurate Prediction of Structural Dynamics for Systems with Isolated Nonlinearities. This one was penned by an impressive team: David A. Najera Flores, D. Dane Quinn, Anthony Garland, Konstantinos Vlachas, Eleni Chatsi, and Michael D. Todd.
That's a power-packed team right there, and the technology they're working on could bring about some amazing breakthroughs. But before we dive into the meat of the paper, I'd like to give a shout-out to all of our listeners who've been following our podcast. We couldn't do this without you.
Absolutely. Special thanks to everyone who's been hiking with me in spirit and imagining all those techie goodness with Shastya. All right, let's get started. Shastya, can you give us a bit of an overview of this paper?
Sure thing. So, imagine you have a structural system. Think bridges, buildings, or even spacecraft. These systems often have localized nonlinearities, like joints or sections that behave differently from the rest. The trick is, those nonlinearities can mess up the dynamics for the whole system, making it incredibly complicated to predict how things will behave under different conditions.
Ooh, so we're talking about those sneaky little areas causing trouble in what would otherwise be a well-behaved structure. It's like shaking hands with someone whose hands are covered in oil. Suddenly, the whole dynamic changes.
Exactly, Aubrey. So to tackle this challenge, the authors propose a machine learning framework that keeps the overall structure's integrity while accurately predicting the dynamics caused by these localized nonlinearities.
Interesting. Machine learning always sounds so magical to me, like waving a wand and suddenly everything's predictable. Could you be more specific about how they make it work?
Of course. They use a multi-layer perceptron, MLP, which is a type of artificial neural network. The idea is to train this MLP specifically to predict what they call deviatoric forces. These forces are essentially the troublemakers, the nonlinear influences at the boundaries between linear and nonlinear regions.
And this MLP, once trained, can predict these forces without having to simulate the whole structure in complex numerical detail.
Bingo. This approach saves a ton of time and computational power. By focusing on the nonlinear regions specifically, the predictions are efficient and scalable, which is crucial for real-time applications like structural health monitoring.
Okay, got it. So instead of painstakingly simulating the whole system every single time, the trained MLP zeroes in on those nonlinear areas, saving everyone a headache.
Precisely. And the cool part is that once the model is up and running, it can handle various initial conditions and external forces without needing to be retrained. Imagine a smart assistant that just gets smarter over time and needs less babysitting.
Haha, that's my kind of assistant. This has huge implications for digital twins and proactive maintenance, right?
Absolutely. Digital twins are like virtual replicas of physical systems used for monitoring and predicting performance. With this framework, you're not just dealing with static twins, but ones that adapt in real time, which is incredibly useful for predicting structural health and planning maintenance well in advance.
That's like having a really advanced fitness tracker, but for buildings and structures. How did they test this framework?
They ran experimental simulations on a simple model with cubic nonlinearities and hysteretic damping. And guess what? The machine learning model nailed it, showing high fidelity to the original system dynamics even under different scenarios.
All right, Sounds like they've really hit a home run here. And the implications go beyond just academic curiosity. We're talking potential cost saving and improved safety, pretty big deal if you ask me.
Couldn't agree more. As someone passionate about making technological solutions accessible and impactful, this paper really speaks to what's possible when machine learning meets engineering.
One last bit before we wrap up, any notes on future research or limitations they've recognized.
The authors are honest about ongoing work focusing on further reducing the reliance on observable boundary data. They're also exploring reduced order models for the linear systems and how to optimize the network architecture to better incorporate unknown nonlinearities.
Pretty riveting stuff. Well, that's all the time we have for today. Thanks for breaking it down with me, Shastya.
Anytime, Aubrey. This was a blast, and I hope everyone listening learned something new and exciting.
Thanks for tuning in to AI at the Edge. If you liked this episode, be sure to subscribe and leave us a review. We'd love to hear your thoughts and what you are interested in us covering next.
Until next time, stay curious and keep exploring the world, both the physical and the virtual. Bye, everyone.
Microphones on, we're ready to go. Talking about AI, don't you know? Neural networks and deep learning too. In this podcast, we'll break it down for you. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data science models, we can't get enough. This podcast rocks, it's never too tough. Got questions, we've got the scoop. Join our tech-savvy podcast group. From beginners to pros, come one, come all. Machine learning's fun, we're having a ball. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data science models, we can't get enough. This podcast rocks, it's never too tough. Machine learning, oh what a thrill. Discussing algorithms gives us a chill. Data sets models, we can't get enough. This podcast rocks, it's never too tough.